comment on what Martin just told us, that is referring to the eclipse on 1970. And I would like to stress the importance of finding this Lyman alpha line and interpreting, because this was the base of all the work that we are doing in UV coronagraphy with UVCS, and hopefully with Solar Orbiter and METIS, and therefore it gave birth to a very, for us, interesting field of research. Now let's go back to the solar maximum years. These were the 80s, and where should I point to this?
Right-hand side. The right-hand side, it should work.
Ah, the right-hand side. I was doing the left.
If you will, go back.
No, we don't want to go back. This was a very interesting satellite, of course, because it was the first one I was involved in, and therefore it was very interesting. And it was the second large observatory for space solar physics, and it was fully dedicated to flares. It was launched in 1980, and after 9 months we lost the pointing capability, therefore it was repaired and released. Now it is a normal thing to do this. This was the first satellite that was designed to do this. And so it was quite an exciting adventure, and it was designed for being serviced by a shuttle, but the shuttle was not yet flying, and this happened 3 years later in 1984. Here we have the manned maneuvering unit. It was an armchair. The astronaut went close to the satellite. It didn't work quite well at the beginning. Actually, it was even dangerous, but then it was possible to retrieve the satellite with the arm and repair it. So it was quite adventurous. But let's go back to the role of Alan in SMM. He was the PI of XRP, the soft X-ray polychromator experiment. It was a joint collaboration of Calum Laboratory, now Rutherford Laboratory, MSSL, and Lockheed. And Alan was one of the 3 PIs. I think this was the only instrument that had 3 PIs in the history of space. And I had the chance visiting Calum to see FCS just a few days before it was shipped to be integrated in SMM. As you see, there were other 6 instruments, all very new and innovative as a concept. And XRP was really consisting of 2 instruments, the BCS and the FCS. I will talk more than everything else about BCS. They were covering from 1 to 22 angstrom. And one was just spectra, but at very high end spectral and temporal resolution, and the other could also take raster, and here you have an example of this kind of raster. Now SMM had a lot of new results that were concerning. For instance, it was the first time that it was possible to take images up to 30 keV hard X-rays and see where the accelerated electrons were impacting in the chromosphere. There was the first gamma line spectra. At last, it was understood that the solar constant was not constant with ACRIM. Now it's normal, but at the time it was a discovery, of course. But I would like to concentrate on this. I wrote the first spectra. This is not exactly true, because there was also a P78 satellite with Solflex of NRL, and there was a Hinotori, the first Japanese satellite of a very interesting and important chain of solar physics spacecraft. But XRP was the only experiment that was really complete, looking at many of these spectra. Here we have an iron 25 spectrum, the observation and the fitting. And what it was important is that I'm sure there are a lot of atomic physicists here, so they will talk about the diagnostics and the capabilities of this kind of spectra. I would like to concentrate to the bent crystal, and it was very important that because of this particularity of this instrument, it was possible to take simultaneous detection of the full spectrum, the resonance lines, the satellite, the forbidden, and so on, of calcium-19, iron-25, and iron-26. There were many other lines, but these were the ones that brought to the results I would like to talk about. And here I retrieved some of tables handwritten by Alan showing all the atomic physics that was going into program that had to be simple and fast to be used during operations. And these programs, you see here the observation, here the synthetic spectra, had to be fast because we had a very limited capability in terms of accessing the computer. It could be done 1 hour, 2 hours a day when we were lucky because the computers were very few. And it was not possible to run heavy codes on them. And these programs were developed on the basis of all the input of Alan Gabriel, who was coordinating a very involved group, a very big effort in Europe done by Françoise and Jacques Dubois, Sergio Volonté, and their collaborators. And then Jacques in the summer came to Goddard and helped to finalize and make this program more flexible. And now I would like to concentrate on 2 results. One was chromospheric evaporation that was discovered with XRP. And when there are the 2 foot points bright in hard X-ray, that is, we are during the acceleration, the primary energy release and the acceleration of particles, we see that the active, this is a differential emission measure of the active region, starts, we have the origin of a source which is 20-25 million degrees, and then the flare decays, and this soft X-ray region disappears again, and we have again just the differential emission measure of the active region. So this spectra gave the possibility to explain this formation of the soft X-ray source. And here I retrieved a piece of paper that was on the first flare that was observed. At the beginning, it was difficult to observe these flares. First, because the sun was not very cooperative. Second, because we were not very good. We didn't yet develop the skill to point at the right region, I should say. But at last, the 29th of March, 1 month and a half after, we had a decent flare. And here we have an analysis, this and the writing of Alan, and here you see this sentence. What it was found is that there was a blue wing in calcium-19 that was showing upflows of 300 kilometers per second. This was the key. And if you see, it doesn't last much, from 1802 to 1817. And XRP and BCS of XRP was able to pick up this because it was fast. You didn't need to rotate the crystal to make the spectra. So you had simultaneously all the lines in order to analyze the data. And moreover, here you have the observed plus fitted, and here you have the 2 components. And you see that if you take into account correctly the satellite lines that were computed by the atomic physics group, then you really can find out this little blue shift that is very important because it's the one that gives you the soft X-ray source. And if you do an analysis of the mass and energy that you input in the corona, you really find it is enough to make, now chromospheric evaporation is given for granted, but indeed at a certain point it was not. I point just to another result because we have not much time. There were many results, but that was that before the impulsive phase occurs and before we observe the blue shifted lines and these upflows that are filling the corona with this new source of soft X-ray, we see a broadening of the line. So there are vigorous non-thermal motions, again 200, 300 kilometers per second, and this was interpreted as evidence for not chromospheric evaporation, but magnetic reconnection going on. But at the time, not as at the present that everybody is invoking magnetic reconnection. At the time, it was not fashionable, so it was not very much really, it took some time in order really to understand that this was going on at the beginning of flares. And there was also the first observation of iron 26. And I think these are the two main results, and it was possible really to achieve this because of the instrument that was had such an incredible time resolution because of the bent crystals, and because of this powerful tool of this atomic data that allowed to really compute very well, reproduce very well what had to be the spectra emitted by the sun. Another thing of SMM that was very interesting was that we had this experimental operation facility. Here there are a few people that took part in this. Therefore, SMM was important because it was the first application that could be serviced by the shuttle. It was pointing here and there on the sun to chase flares. There were inter-instrument flags. These concepts are taken again by Solar Orbiter, and this is why sometimes I'm skeptical about them, because it was difficult for SMM when we could each hour to send commands. So I am a bit skeptical, but anyway, it is good to do it. And then the important thing was that it was the first time that at Goddard there was a large community of resident solar physicists, and we were in touch with all the observatories, and at the time even with the Russian observatories, and also the Chinese took part, although very little, to this effort. And if you think at the time, it was 1980, so it was very early in the game, and it was not easy. But I think the solar physics community was a pioneer in the global collaboration. Here is a planning, and I want to show this because you see there was Dave Spike in the morning from NOAA telling us how complicated was the magnetic region that we could select. We were selecting the coordinate. Here you see a blackboard that is totally empty, and then we were filling it with what each instrument would have done. Here is the first stuffing chart. We started the 17th of February in working for the planning of XRP. And here you should see that there is written somewhere JOS, or here, I don't remember where. And these were the ancestor of the jobs of SOHO. So you can really find that this was the preceding very much SOHO and Solar Orbiter in many of the things that we were doing. Here is the team in its beauty. Lauren Acton, Pete Strong, Bob Bentley, Johnny Bacher, Ken Phillips, Jack Wilson, Chris Rapley. And it was the day in which Margaret Thatcher came to visit us at Goddard, and to visit the two English teams that were working at XRP. I arrived so late that I didn't meet her, but anyway. But that was a point of respect of the work that the scientists were doing, and I think. And thanks, Alan, and as you see, the sun is in front of you.